All right, so now that we have a sense for the features of the ocean floor, we're going to ask an even more fundamental question. What's going on with the oceans themselves? Why do we have oceans that pool into ocean basins? To look into this, we're going to have to learn about this concept of isostacy. This is going to explain why we're not underwater right now. But to understand how this works on a global scale, we're going to have to compare the properties, the mechanical and chemical properties of continental versus oceanic crust. Finally, we'll learn how isostacy or isostatic adjustment is influencing Earth's elevation right now. So let's start off with a quick calculation just to set the scene. We know the volume of the ocean overall. It's around 1 billion cubic kilometers, or 1,000 million cubic kilometers. We know the surface area of the Earth, 500 million cubic square kilometers. And so we can ask, what's the average height of the ocean? What would the average height of the ocean be if Earth was a perfectly round planet with no topography, right? So this is basically, 1,000 divided by 500, 2.65 kilometers tall. That's how tall the oceans would be if there was no ocean basins or mountains or tall standing continents. We'd all be underwater right now. Life would be very difficult. But fortunately, that's not the case. We all know this. The ocean collects in deeper basins, and we're sitting up here on the high continents, not underwater. And we can see this when we look at Earth's topography. The ocean collects in these low-lying ocean basins that sit on oceanic crust, versus on the continents where most people live. These are tall standing and dry for the most part. So we can look at this elevation data of Earth in a couple different ways. One nice way to sort of show the rarity of certain types of elevation is through this what's called a hypsographic curve right here. Hypsographic curve. This is basically going to show you the percent area, the percent of Earth's surface at certain elevations here. So elevations on the y-axis. And we're going to start off with the highest mountains. This is Mount Everest. This is some of the Himalayas, some of mountains in South America. There's not very much of Earth that's 4,000 meters above sea level here, only maybe 1% or so. And then we have this increase in cumulative area, but a decrease in elevation down to sea level here. So this puts us to around 30% of Earth that is, above sea level on a continent. There's some part of continental shelf that increases this number a little bit. Continental slope maybe gets us to 40%. And then we're down in the abyssal plains. This is, the ocean basins that cover, 40, 50, 60, 70% of Earth's surface. And then there's this much smaller part, much less than 5%, that's deep enough where it sort of qualifies as a deep ocean trench. And so you can look at this data as a hypsographic curve, but you can also look at this as a histogram. That's just counting how frequent is every depth bin on a global map of Earth. And what you see are these two groups that form. One is the abyssal plains. That's sort of the most common ocean floor elevation. And then there's the continents here. This is just above sea level. That's the most common continental height. So really, Earth has these two different types of surfaces, continents and ocean floor. One of the cool things is that this is quite different than our neighboring planets. You can see this is a similar histogram here for Earth. You see the continents up here. You see the ocean floor, the abyssal plains down here. If you compare this to Mars or Venus, these only have one peak. With Venus, this is really prominent. There's not a whole lot of topography gradients on Venus. On Mars, you can see a bit of this fans out a bit more. There's a lot more variability here, including the highest mountain in our solar system on Mars, Olympus Mons. But there's not these two groups like we see on Earth. There's not an ocean basin and a continental crust that we see. And actually, if you look at the surface of Mars, it's actually really interesting because one hemisphere is just a lot lower than the other one. And the one, this lower one has very few craters, and this one has a whole bunch of craters. So quite different than Earth. We've actually been to Venus and sent probes to Venus, and the surface of Venus you can see is it's all something that looks like basalt. It's all this dark rock. It looks very similar to the rock that we can see exposed in certain parts of Hawaii. It's also basalt, and it looks similar to the deep ocean crust, which is also basalt. So that one really prominent peak in elevation for Venus that sort of corresponds to the ocean floor part, and then it's really the continents that are unique on Earth. So before we start to figure this out, let's review what Earth looks like in its interior. Previously we went over that Earth has an inner core, an outer core. The inner core is solid, the outer core is liquid iron. Then we have the mantle, and the mantle can be divided up into its mechanical layers. The mesosphere, which is rigid and solid. The asthenosphere, which is more, sometimes this is called weaker. That's really what asthenos means. Sometimes you could call this plastic or ductile. Sometimes I like to think that it's almost like if you have if you take some butter out of the fridge and have it sit on the counter for a while, you can feel it flow. Even though it's still a solid, it's still able to be deformed and moved. And anyway, then on top of the asthenosphere lies the lithosphere. The lithosphere is a sort of combination of the upper mantle and the continental and oceanic crust that sits above it. So this is sort of the outermost organization of Earth. But essentially you have this solid lithosphere here that sits on this deformable, sort of movable asthenosphere, even though both are still technically solid. So both the oceanic crust and the continental crust sit above this upper mantle asthenosphere. And so why are the continents taller than the oceans? There's two main reasons for this. One is that the continents are thicker than the oceans. So the continental crust is around 35 kilometers thick. The oceans are around 6 kilometers thick. And also the dominant rock type in the continental crust is very different than the ocean. The oceans are mostly basalt, which has a density of around 2.9 grams per cubic centimeter, whereas the continental crust is composed mostly of granite. And granite is a rock that it's usually cooled over really long periods of time. Usually this is underground, and so the magma sort of cools over millions of years, and that's enough time for these different crystals to sort of emerge and form, and that's why granite has this kind of pockmarked modeled approach, modeled view, versus basalt is just sort of solid black. But anyway, the density of this granite is less than oceanic crust. It's around 2.7 grams per cubic centimeter. And then, underneath both of these, the asthenosphere has a density of around 3.3 grams per cubic centimeter. So you have this organization where you have the most dense thing on the bottom, and then you have the oceanic crust and the continental crust essentially floating on top. And so one of the ways we know this, the thickness of these different layers is through seismological investigations. These can be separated into active seismography, so where you have an actual source of a wave. It's usually these air guns that are fired off the back of research ships. These create these waves that travel down, and some of them reflect back off of the ocean floor and hit these receivers. Some of the waves pass through the sediments and reflect back off of the crust back here. Some of them reflect back off of the upper mantle boundary and come back here. And so by working up these different return times for these different seismographical signals, you can sort of look at the structure and the thickness for the different layers of ocean crust. Based on how fast it takes the waves to get back to you, you can learn something about the density of these parts. So this is where this information comes from. And I should mention that the natural earthquakes are also a good resource. If you have an array of detectors, you can do a lot of this mapping without setting off explosions, which is actually favored now. So doing this process sort of around the world and integrating the data, what we find is that not only is the oceanic crust thinner than the continental crust just about everywhere, but the continental crust is actually thicker in the regions that we associate with mountains. There's two areas that really pop out on this map. The first is the Himalayas. Over here you can see that these are over 70 kilometers thick. Same for the Andes as well. This thickness is way, way bigger than the actual height of these mountains. Most of this is actually digging into the mantle. So these are really tall blocks of earth. Only a small part is actually exposed in the high elevation mountains. So in this way, the continental lithosphere sitting on the asthenosphere is like an iceberg floating on the ocean. Both are regulated by this process called buoyancy. That's why they float. Buoyancy is the ability of an object to float in a fluid by displacing a volume of that fluid equal in weight to the floating object's own weight. So the weight of the iceberg is reflected in the amount of water that's pushed up above the level it would have been. But because the iceberg is less dense, it pokes above the water. So that's why 90% of an iceberg is below water, only 10% is above water. There's basically a similar a 90% difference, or a 10% difference in the density of ice compared to water. Importantly, this happens regardless of the size of the iceberg. So if you have a big iceberg, most of it is underwater, and you have 10% above water. Same thing for a smaller iceberg. You have 90% below water, 10% above water, and you have the biggest iceberg sort of represented as the tallest peak. So in the same way, in the last slide, we saw that the biggest mountains have the deepest roots here. So you can see that this might be the Himalayas, and this is the roots of the Himalayas digging down deep into the earth. Okay, so this process, this balance of forces is called isostacy. It has a Greek origin from isos, meaning equal, and stasis, meaning standstill. So the idea here is that you have this equal standstill of forces that lead to the earth as it is. So another way to think about this, if icebergs aren't your thing, are just different blocks of wood. So we can see here we have two different blocks of wood here floating in a pool of water, and different pieces of wood have different density. So for instance, oak is more dense than pine. So what we have here is a representation of the oceanic and the continental crust here. We have a thinner section of a more dense material, that's like the oceanic crust, and we have a thicker section of a continental lithosphere, which is represented here in pine. So you can see that the pine actually digs deeper into the asthenosphere, or the water here, but that's what, would be the asthenosphere if this is Earth, and stands taller here. So we have this formation of this ocean basin here because the oak here is thinner and more dense, and the pine is less dense and thicker. So this isn't just explaining why we have ocean basins in the first place, but this also helps create predictions about how things might evolve over time as a response to different processes. For instance, the Himalayas today are actively eroding because ice comes in, it freezes, it cracks rocks, it turns into sediment. That sediment gets washed out into the ocean. And so the Himalayas, like most mountain ranges, are slowly losing mass over time. As that happens, the weight of this total column decreases. Right? So as you're eroding mountains here and you're pushing it onto a floodplain, then this area gets lighter. This whole mountainous section starts to push up higher and higher. And then in contrast, the area that you just deposited your sediments, maybe it's a floodplain, maybe it's a continental shelf, that area starts to push down because it's got more mass now. So this is a sort of a regulating process, that as you erode, you push up from the roots of the mountain, and then anywhere where you're collecting sediments gets pushed down. These are forces that balance this isostatic readjustment that controls the height of continents over time. So even if you're chopping off the top of a mountain through erosion, this will balance and the roots will come up, and you'll still have a mountainous region. So here's an example about how this isostatic equilibrium process leads to continental shelves. This is the Los Angeles Basin here, and so there's ranges of mountains in the north that are rapidly eroding, and the sediment from those mountains is piling up in shelf areas like this, sort of south of the Los Angeles area. This is an area where there's should be lots of kelp forests that are benefiting from the shallow platform. It's close to the sun, close to light, so they can actively photosynthesize and grow and create this ecosystem. So one of the things that maintains this shallow continental shelf ecosystem is the fact that this part of the crust here, this part of the lithosphere, is getting more sediments from the mountains that are being washed in here. So it's becoming heavier over time, and this is going to be pushing this area down so it can be below sea level. So that's one of the ways that the continental shelves can form and become a bit more depressed than the main plane of the continent. So isostatic readjustment or isostatic equilibrium isn't just formed by erosion, or isn't just affected by erosion. It's also affected by things like melting ice sheets. So you might have seen maps of Greenland here. You always see this big slab of ice. This is a kilometer to 2 kilometer to even 3 kilometer thick ice sheets that are sitting on top of the lithosphere. And so this is all this extra weight that's pushing down on this rock. And so this has been going on for a long time, and so it's actually depressed the center of Greenland. So this is what Greenland looks like without any ice on top. All this part in the center would be below sea level because you have this extra weight pushing down, and so this whole block of lithosphere is readjusting. It's being pushed down, and so that's why the center of Greenland is below sea level. This also is causing certain parts of the Earth to rise today. So, for instance, areas like Antarctica, but also especially in Canada, in Northern Europe, and Scandinavia. These are areas that are being uplifted today at a rate of a few millimeters per year. And this is because previously they were covered in ice. So the same Greenland effect was impacting northern Canada, Scandinavia, Antarctica to a greater degree than today. And because the major ice sheets during the last glacial period, 20,000 years ago, because those ice sheets melted, all this weight has been lifted. It's been pushed elsewhere back onto the ocean. Right? That water is returned to the ocean. It's not sitting on top of Canada anymore. Canada can start rising again. So it's this rebound effect because you have essentially this lithosphere floating on top of this asthenosphere. Okay, so we started this video asking why does the Earth have ocean basins? And really it comes down to the fact that we have two different types of crust with two different densities and two different characteristic thicknesses. Continental crust is less dense than oceanic crust, and so it sits above the oceanic crust. Everything in the lithosphere, continental crust, oceanic crust, this sits above the plastic asthenosphere. So the asthenosphere is like water in the iceberg analogy, but it's still a solid. It's just something that can move around. I said butter before. There's probably some other plastics that you might have seen before that you can kind of move around with your hands when you put enough pressure. That's what's going on here. And because this is deformable, because it can respond to changes in weight, you have this balance here, this isostatic balance between the buoyant forces pushing up and then the weight of the lithosphere pushing down. So this leads to the observation that the highest mountains on Earth today have the deepest roots because they're sort of sinking deeper into the mantle. So overall, we have this process of isostatic equilibrium. This is a balancing act where any change in the weight of the lithosphere because erosion happened or because the ice sheets in that area melted, that change will be balanced by this upward restoring force. There's less weight pushing down so that the asthenosphere will push up more. And so the elevation of that section of crust won't change as much. It'll be restored to some degree. So this process of isostatic equilibrium maintains this balance in the face of things like erosion or changes in ice sheet sizes. And in fact, today, there are large parts of the northern hemisphere that are still rising because of this melting that happened 20,000 years ago at the end of the last glacial period that is, relieved this weight over Canada and causing that part of the world to rise up. And this is actually really important in figuring out how fast sea level will rise. And this will come up later in the semester.